Hi, everybody. I'm Giovanni da San Martino. I recently joined the department as an assistant professor, and I will teach the course of machine learning at the degree of data science, the master degree of data science. So today I wanted to talk a little bit about machine learning, and I will try to say basically a couple of things. One is try to convince you why it is important to know something about machine learning nowadays. And then I will try to tell you a little bit, in couple of slight detail, what is machine learning. So we just go, we introduce a couple of concepts. So, so let me start. I have this clickbait, little bit clickbait title. So let me start by explaining it. What do I mean by it? So like, if you think about the first industrial revolution in the 18th century, what happened is that physical labor was replaced by machines. So there's been this big switch, and there's been like an increase in productivity and so on, and scalability. Let me use this term. So then the question now becomes, like now in the present days, will artificial intelligence and machine learning actually, will they replace the mental labor, like intellectual labor, on the other hand? So is there a parallel between the two? And actually, this is why many people consider that the machine learning will revolutionize our society. So, so first of all, this is kind of complex question to ask, and I just wanted to make a couple of points, and I will use an example for this. The first point is this question doesn't ask whether machines will be capable of having very intelligent behavior. The question is about something else. It's about whether they will be able to replace some of the jobs that today can only be done by humans. And the other point that I want to make is that this is not yes or no questions. There's going to be like a progressive switch probably. And I wanted to, I heard this interview, I put a link here on YouTube of an Italian startup called Translated that it is about, as the name suggests, machine translation, so automatically translating a document. And their business goes like this. They get a document, they'll translate it automatically, and then they give it to a professional translator to do the final editing. So when they started, they say in the interview that when they started, the translator were complaining all the time about the quality of the automatic translation, and they were just wasting their time doing a lot of work just rewriting the translations. But with time, they started to have to increase the accuracy with the feedback of the translators, and receiving more data and improving their algorithms. And they get to a point in which the professional translator just have to do some quick editing here and there. So it has been like a continuous process. There's not been a day in which there's been a sudden switch. The other point I wanted to make that this idea of tiny improvements is in the case of this company, it has like it's a relatively small company, and it interfaces with professional translators, so the size has naturally is very small. But nowadays we have examples of many companies that rely heavily on machine learning for some of their core business. For example, you have Netflix that has a recommendation system that suggests you what to watch next, or like even Spotify, similarly what to listen to next. And you have companies like Google and Facebook, which base their business on selling you advertisement. And it's on their interest to sell you the right advertisement, the ones that will make you do the more clicks. In these cases, this company they have a huge market. Obviously, they cannot rely on manpower to do personalized suggestions. So they have to, this has to be an automatic process. And this is why machine learning plays an important role. And even in these cases, even tiny improvements, given the huge market that this company have, like even like an improvement in accuracy to 0 point something %, like for Google or Facebook, that might turn out in millions of additional revenue. So, so machine learning, that's why machine learning plays a very important role. So you know most of these companies or these products. You heard about self-driving cars for sure. Maybe you haven't heard about Two Sigma. Is a company working on the financial markets. It uses machine learning to support their predictions on their hedge funds on what stocks to buy and so on. And maybe you might have, I'm not sure if you have heard about IBM Watson, which was a system that used to play the Jeopardy, which is a trivia style quiz. And he was able to beat the all-time champions. Same thing happened with AlphaGo. So first simple reason to motivate you to deepen your knowledge in machine learning. These companies are hiring like crazy people that are experts in machine learning, and this is going to be good for your pockets. Okay, so let me go to the second part. Let me give you some ideas on what is machine learning. So I started with a question about the Industrial Revolution, making a parallel between the first one and the current times. Let me do something similar here. So going from traditional algorithms to machine learning algorithms. You all, I'm pretty sure you all know what is an algorithm. It's a clear and ambiguous description of a set of steps to solve a problem. It's a recipe to solve problems. So what happens if we are, let's say we have an algorithm to do the division between numbers. We have an input, so a division that we want to make. We put in our computer, and almost instantly we get in output the correct result. So there are these three elements: the input, the algorithm, and the output. Keep this in mind for a minute. Okay, what happens when we don't know the recipe to find a solution of a problem? Okay, there's nothing we can do. We don't know the solution, there's nothing we can do. But there are some problems that us as humans are able to solve easily. For example, if I give you this problem, if I give you an image and I ask you, do you see a tree in this image or not? You're going to be able to do this. This is going to be an easy job for us as humans. What is going to be hard is to write down an algorithm to solve this problem. So how can we do it? For example, we can try and say, we need to write the algorithm in such a way that the computer understands it. So the computer understands the images as a set of pixels. So numbers that represent the colors of the small squares in the image. So if we have to tell the computer what is a tree, we can describe patterns of pixels and says which one of these correspond to are indicators that there's a tree and which ones are not. So we can say, you know, there's some green, there's some brown below it, and maybe something like that is going to be, we can make some examples that this is going to be a tree. Something, if you have different patterns, maybe you say there's no tree. Yeah, it's not that simple. There are so many cases. There are different lighting conditions. There are cases in which there are no leaves because the way the picture is taken. There are trees that have no leaf. There are the same tree in a different season shows different colors. There are trees with a different orientation. So you need to take this into account. This one I would recognize as a tree, but it's green and blue. So if you really start to do this exercise by hand, you get crazy, and you don't. It's really long, unless you have unlimited time and unlimited space. If you have both conditions, yes. If you spend a whole eternity listing all these patterns, and at some point you cover all the possibilities, and that's it, and then you're done. But we are finite being, and we don't have. Hopefully, we want to spend our time also doing something else. So we cannot do this. We need to find another way. So let's try to find a simple loophole. Okay, I define my pattern as the whole image. I take the whole image, I database. I don't know how to answer. Again, if I have enough time, I can have a huge database, and that is fine. If I don't have enough time, I'm going to run into a problem. I cannot generalize to unseen examples. So having this loophole of just listing the images, so memorizing the input examples, in other words, doesn't work. It's like when you have to study for your exams. It's not a good idea to memorize the exercise. You need to understand them, because otherwise you're not going to be able to do the new one on the day of the exam. Okay, then what we can do? The idea is we need to go back and find these patterns. That was my first proposal. But instead of doing ourselves, we can ask the computers to do it for us. And we can set up the problem in this way. We can still have an input, which is our image, as before. We can define an output, which is like, say, 1 if there's a tree in the image, 0 if there's no tree in the image. And then I can ask the computer to determine automatically what are the patterns. So I ask him, look for all the patterns, do a quick search in all the space of patterns, or maybe like a reduced space. That's even better. And you look for the ones that appear in one class, so when they're correlated with trees, but not in the other ones. So these are indicators there is a tree and so on. And then the computer can make us, maybe in a reasonable time, this list, and then we can use this one. So if you compare this image with the previous one, you see the elements are rearranged. So the input is still here, but here before there was the algorithm that goes in, and we have the output. Now what do? We take the input, we take the output, and we try to devise the algorithm, which in our case, in our example, is this list of patterns of pixels. So this is the difference schematically between classical algorithms and machine learning ones. Okay, so let me go a little bit, let me add something. Let me complicate things a little bit. Okay, so let's try another example. Let's say that I have as input values that represent the weight of something, and I want to predict the corresponding height. So I have this list of points, and I want to be able, given any value for the weight, to be able to predict what would be the correct height, whatever that means. In machine learning, we usually do one thing. We take our data and we divide it in 2 sets. It's going to be clear why in a second. The one set is called a training set, and this is the set of examples that in which I search my patterns. The set of pixels of the image, or in this case, these points, the parameters of my model. And then we have a test set that we're going to use in the end, just to have a confirmation of how good was this model that we found, like a further confirmation. We don't use this one for statistical reasons, and this is going to be clear when you attend the courses. Okay, so we want to infer what is the right relationship between these 2 variables, the input and the output one. We need to choose, so basically we are going to do a fitting in this case. I'm really simplifying things here. And we need to choose the shape of the fitting. So for example, we can have just a linear fitting. These points are my training set, and I take the linear fitting that best fit the set of points. Let's say that this one is, believe me, that this is the one, the line that that is output. If I then try to see how good is this line, how good means like how, what is the distance, average distance between these points in this case. I can see how good it is on the test set and say that the performance are kind of the same. In this case, the line, as you can see, is kind of simple, model, and is not able to fit perfectly my points. And this is translated to say that if I take a linear model, it has a low bias because it's not really able to fit well the points in the train set, which is not necessarily a bad thing because we are not sure. It might be the case that these measurements are there's some noise in the measurements. For example, the person who take these measures maybe was short-sighted, so he made some mistakes here and there. So maybe we shouldn't trust 100% all those points. As you can, and then you can see, you can take a more kind of logarithmic style curve, and this seems to be fitting more our training points. And then, okay, so if we take a more complicated curve, this seems to be fitting more our points. So can we push this further? Can we have like complicated lines that fit perfectly, that is very squiggly and fit perfectly my training points? Yeah, why not? This is a bad idea for this for the same reason. I'm trying to give you an idea here. So if I take this, if I learn this line on our training set, and then I try the same line on our test set, so just the green points, while this fit perfectly our training set, it makes quite an error on the test set. So only fitting our training set is not the best strategy because there are other points we are not considering, which are like the points like which I was referring to as like those examples that they're supposed to generalize to when we're supposed to generalize to unseen examples in which we want to perform as well. So having a very complicated line is not a good idea. And in this case, just again introducing some terminology from statistics, we would say that this type of curve has high variance because if we change the set of points of our training points, the curve will change a lot. While the linear curve, as we've seen, doesn't really change much because it's not powerful enough to adapt to the training data. This one seems to be has more freedom to adapt to the training data, but to the detriment, in this case, of accuracy on the test data. So the main message here then is that the first algorithm that we have seen, the one about the images, I was just saying we try to find this correlation that best fit our training set. Here in this plot that I've just shown you, I try to give you the idea that fitting the data that we have is not enough. We need to ensure that we are going to perform well on data that we have not seen. And there are lots of mathematical formulation to express the relationship between some models and their capacity to generalize to unseen data. But in general, so we need to make a choice on what type of model we want to use. So if we go back to this example, what type of curve we want to use? If it's a linear, if it's the second one, parabolic curve, or if it's the one that's very powerful and fit all the points. This is a choice that we need to make before, and usually this choice is made in such a way to avoid this case, because it does not give guarantees on data that we have not seen. There are many of these assumptions, and as I was saying, all of these have associated their own generalization bounds on data that on unseen data. These assumptions lead to many different algorithms, and each of these will be each of these will be optimal according to how well the assumption fit the real real data that we want to actually predict. So, in other words, there's unlike other fields, there's no an algorithm that is better in all possible contexts. Depending, actually, there's a theorem called the no-free lunch theorem that says that if we take a machine learning algorithm with its own assumptions, again, to limit the power of the model, we can work out against this assumption and make it create a task on which it performs really bad or really good. So this is to say that, again, that the machine learning field is a very big field for this reason. There are many different algorithms that work in different contexts, and it is important to get a feeling of which one works well in certain conditions. So another point I wanted to make, I'll try to be brief now, is about big data. So nowadays, many learning problems can use very large amounts of data, and this implies that the algorithm that we implement needs to be extremely efficient in dealing with the data, with this data. So this is also important to be able to code very fast, to have very fast code, or to know which libraries to use. And one last point is, if you remember the slide with all the applications and the companies. So since nowadays machine learning is used in so many different applications, so many different contexts, the simple performance of the simple accuracy of the model is no more the only measure to take into account. So for example, in some contexts, it is very important to understand how why a model took a certain decision. So we need to be the model needs to be able to explain. This is as important as to be able to explain why it takes some decision. It is as important as actually the accuracy of the decision itself. If you think about a system that should support doctors in their decisions, the doctors will never trust the system. They just say do X or do Y, unless it explains the whole reasoning that took him there. Okay, so to conclude, just to say that so my points here in this talk were to say that nowadays machine learning is the core of many internet companies, and they do a lot of they invest a lot of in machine learning, and machine learning is nowadays used in very large number of different applications, some very far away from the other. And I hope I give you an idea of how vast and complex is is this subject to study. Thank you.